If you've ever bought a bag of plastic dinosaur toys, there's a very good chance one of them isn't a dinosaur. It's got the sail on its back, the reptilian sprawl, the toothy grin, and it usually gets shelved right next to Tyrannosaurus and Triceratops without a second thought. Dimetrodon. And here's the thing worth sitting with before we get into anything else. It's not just technically not a dinosaur in some minor taxonomic footnote sense. It's not even close. There's a peer-reviewed academic paper published specifically for classroom use, literally titled Dimetrodon is not a dinosaur. And once you actually look at where this animal sits on the tree of life, the punchline gets a lot stranger than a simple correction. Dimetrodon is more closely related to you, personally, than it is to any dinosaur that ever lived, or to any lizard, snake, turtle, or crocodile alive today. Let's start with who actually found it and named it, because even that story has its own tangled identity problem. Fittingly enough, the genus Dimetrodon was formally established in 1878 by Edward Drinker Cope, working in the thick of the so-called Bone Wars, the notoriously bitter, competitive scramble for fossils that defined a big stretch of 19th century American paleontology. Cope named 3 species that year, based on material collected from the red-colored Permian rock of Texas and Oklahoma, land that would go on to produce the overwhelming majority of Dimetrodon fossils ever found, across what are now called the Clear Fork, Wichita, and Pease River groups. But the very first Dimetrodon fossil had actually already been described a year earlier, in 1877, under a completely different name, Clepsydrops limbatus, and it wasn't formally reassigned into the genus Dimetrodon until 1940, more than 60 years later. Go back further still, and there's an even older specimen sitting in the record, a jaw fragment found all the way back in 1845 on Prince Edward Island in Canada, described in 1854 under yet another name entirely, Bathechnathus borealis. That fossil wasn't recognized as a species of Dimetrodon until 2015, and the naming authorities responsible for policing scientific names didn't formally rule in favor of keeping the more familiar name Dimetrodon over the older, more obscure Bathechnathus until 2019. So even the discovery history of this animal is a long chain of things getting misidentified, filed under the wrong name, and eventually sorted out decades, or in some cases, centuries later. It's a pattern that, as you're about to say, runs straight through the rest of this animal's story too. One more genuinely non-North American wrinkle worth knowing. In 2001, a smaller species, Dimetrodon teutonus, was described from the Bromacher locality in Germany, the only confirmed Dimetrodon material ever found outside North America. The name itself is worth pausing on, because it's more precise and slightly less precise than it sounds. Dimetrodon means 2 measures of tooth, from the Greek for 2, measure, and tooth, referring to the fact that, unlike most reptiles of the era, which carried a mouth full of more or less uniform, peg-shaped teeth, this animal had teeth of clearly differentiated sizes and shapes. Small incisor-like teeth up front, 1 or 2 much larger, blade-like canine teeth further back, and smaller teeth again behind those, plus a set of teeth lining the roof of the mouth. That's genuinely 3 distinguishable tooth types, not 2, which paleontologists have half-jokingly noted would technically make Trimetrodon the more accurate name. But the underlying discovery matters more than the naming quirk. This kind of differentiated dentition, called heterodonty, doesn't show up in the reptiles Dimetrodon shared its world with. It shows up here first, in this specific branch of the family tree, and it's considered an early, comparatively simple, precursor to the much more elaborate incisor canine molar tooth specialization you'd find in a modern mammal's mouth, your own included. Which brings us to the actual heart of the myth busting here, because that detail about mammals isn't a throwaway comparison. It's the whole point. Dimetrodon belongs to a group called synapsids, animals defined, at the skeletal level, by having a single opening in the skull behind each eye socket. Dinosaurs, along with modern lizards, snakes, and crocodiles, belong to a different group entirely, called diapsids, with 2 separate skull openings instead of 1. That single versus double opening split reflects a genuine, deep evolutionary divergence, one that happened around 310 million years ago, back in the late Carboniferous, when the ancestors of synapsids and the ancestors of everything we'd recognize as a modern reptile or a dinosaur went their separate evolutionary ways. Synapsids are, specifically, the lineage that eventually produced mammals. Dimetrodon sits as the closest known relative to Therapsida, the group containing the direct ancestral line to every mammal alive today, humans included. So the claim isn't just that Dimetrodon happens to not be a dinosaur, it's that the branch of the tree it sits on split off from the dinosaur and modern reptile branch tens of millions of years before dinosaurs existed at all. And that branch runs directly toward you, not toward anything currently wearing scales. You'll sometimes still see this whole group referred to, in older books and documentaries, as mammal-like reptiles. That term is considered outdated and genuinely misleading by current researchers, since Dimetrodon isn't a reptile that happened to resemble a mammal. It's a much earlier, more primitive branch of the actual mammal lineage itself. The current preferred terminology is stem mammal, or more technically, non-mammalian synapsid, language that puts the emphasis in the right place, on ancestry rather than superficial resemblance. And the timeline gap involved is worth stating plainly, because it's the detail that makes the dinosaur toy aisle mistake genuinely strange, rather than just a minor labeling error. Dimetrodon lived during the Early Permian, roughly 294 to 271 million years ago, and appears to have gone extinct around 272 million years ago, during a mid-Permian extinction event. The earliest dinosaurs that most paleontologists confidently agree actually qualify as dinosaurs, animals like Eoraptor and Herrerasaurus, don't show up in the fossil record until around 231 to 230 million years ago. That's a gap of roughly 40 million years between Dimetrodon going extinct and the first dinosaur ever existing, even if you're generous and count a more fragmentary, disputed possible early dinosaur relative from around 243 million years ago. You're still looking at a gap approaching 30 million years. Dimetrodon didn't just fail to be a dinosaur. It was already long gone before the earliest dinosaurs showed up to replace it. Now, the sail, because it's the single most recognizable feature this animal has, and it turns out to be genuinely, actively debated among the people who study it professionally, not settled the way most textbook illustrations imply. The classic explanation, first proposed back in 1940 by Alfred Romer and Llewellyn Price, is thermoregulation. The idea that the tall array of elongated spines running along Dimetrodon's back, connected in life by skin, functioned essentially as a solar panel, increasing surface area to help the animal absorb heat faster in the morning and, depending on blood flow, potentially shed excess heat later in the day. Several biomechanical studies through the 1970s, 80s, and 90s built physical and computer models, supporting some version of this idea, generally agreeing the sail was reasonably good at speeding up warming, though less clearly effective at actually shedding heat once the animal got too warm. More recent work has complicated that picture considerably. A 2010 study led by Adam Huttenlocher pointed out a real problem with the pure thermoregulation story. Some of the smallest Dimetrodon species also carried prominent sails, despite the fact that small-bodied animals already exchange heat with their environment efficiently on their own, without needing a large external radiator to help. That same study noted that a close relative, Sphenacodon, had only a low ridge along its back instead of a tall sail, suggesting the structure likely evolved gradually from something that wasn't originally built for heat regulation in the first place. Then in 2010, a separate study led by Robert Tompkins ran a detailed allometric analysis, essentially checking whether the sail's size scaled with body size, the way you'd expect if its job were purely functional heat exchange. It didn't. The sail grew disproportionately larger in bigger individuals and larger species, a scaling pattern the researchers found comparable in magnitude to how antler size scales with body size in modern deer. A textbook example of a trait shaped primarily by sexual selection rather than practical survival function, combined with existing evidence of size differences in the sail between presumed males and females of at least one species. Their conclusion leaned towards sexual display, species recognition, or mate attraction as the primary evolutionary driver, rather than thermoregulation. There's an added wrinkle worth including, honestly. Some broader research on this whole group of early synapsids, suggests they may already have been developing some capacity for internally regulated body temperature, which, if accurate, would make an external heat-collecting sail even less necessary as a primary survival tool, and would push the explanation further toward display. As of right now, there's no fully settled answer. Most current sources describe the sail's function as genuinely uncertain, quite possibly serving more than one purpose at once, with sexual display currently the more favored explanation among researchers actively working on the problem, but not a settled replacement for thermoregulation so much as a serious, still open challenge to it. The teeth deserve one more layer of detail beyond the 2 versus 3 types, naming quirk because there's a genuinely striking discovery buried in them. A 2020 study led by Aaron LeBlanc found that some Dimetrodon teeth carried fine serrations, tiny cutting ridges along the edge, structurally functioning something like a steak knife. That's notable on its own, but the real headline is the timing. These serrated teeth appear in the fossil record roughly 40 million years before anything resembling them shows up in theropod dinosaurs, the group that includes the serrated, blade-toothed predators most people actually picture when they hear the phrase serrated dinosaur tooth. It's a clean example of convergent evolution, two entirely separate, hypercarnivorous lineages, tens of millions of years apart, independently arriving at the same basic cutting-edge solution. Worth being precise about the details, though. Dimetrodon serrations were structurally different from a theropod's, extremely fine and closer to microscopic cracks in the enamel, and they lacked a specific stress-dissipating feature, a small rounded gap at the base of each serration, that theropod teeth like those of Edaphosaurus actually had, meaning Dimetrodon's cutting edge, while superficially similar, was more prone to structural failure under repeated use. And not every Dimetrodon species even had serrations in the first place. A 2014 study led by Kirsten Brink found a genuine evolutionary progression across the genus over time, tracking prey getting larger. Earlier, smaller species show smooth, unserrated teeth suited to smaller prey. As larger prey animals became available, larger Dimetrodon species developed enamel serrations, and the largest species of all developed fully formed denticle-style serrations closely resembling what you'd see in a shark or a theropod dinosaur. Even the German species, Dimetrodon teutonus, kept sharp but unserrated teeth. The serrated bite wasn't a fixed trait of the whole genus. It was something that evolved more than once in step with what was actually available to eat. Speaking of what was actually available to eat, Dimetrodon was the apex predator of its ecosystem, hunting a range of prey documented directly in the fossil record. Freshwater sharks, amphibians, including the strange boomerang-headed Diplocaulus, other early terrestrial tetrapods sharing the same Permian floodplains. There's a particularly vivid piece of fossil evidence tied to this. Excavators found a burrow containing the remains of 8 juvenile Diplocaulus, several of them partially eaten, with tooth marks matching Dimetrodon dentition, one missing its snout entirely, interpreted as Dimetrodon actively digging into a burrow to reach amphibians that had gone dormant underground, likely riding out a seasonal drought and getting caught while defenseless. And there's a genuinely new piece of evidence, published just this year, that adds real texture to the bigger picture of how this animal actually fed. Researchers describe the earliest known fossilized regurgitated pellet from any fully land-based predator, recovered from the same German locality that produced Dimetrodon teutonus, containing the partial remains of 3 completely different prey species of noticeably different sizes, all inside a single regurgitated mass. It's direct evidence of genuinely opportunistic, generalist feeding behavior, an animal working through whatever prey was actually available, rather than specializing narrowly on one type of meal. There's also fossil evidence, presented at a professional geology conference in 2015 by paleontologist Robert Backer and colleagues, pointing toward cannibalism within the genus. At a bone bed in Baylor County, Texas, they documented shed Dimetrodon teeth mixed in with damaged Dimetrodon skeletons, both juvenile and adult, showing butchering-style marks on limb bones and shoulder and hip plates, patterns closely matching damage already known from a related sail-backed synapsid confirmed to have been Dimetrodon prey. It's worth being precise that this specific finding, as far as the published record shows, exists as a conference presentation rather than a fully peer-reviewed journal paper, which doesn't make it unreliable exactly. Backer is a serious, credentialed researcher, but it does mean it hasn't gone through the same level of scrutiny as some of the other evidence in this video. The fairest way to put it is that there's real fossil evidence consistent with cannibalism in this genus, presented by a credible source, short of it being fully settled, peer-reviewed fact. And now, the story that ties this whole episode together, because it's an almost perfect mirror of exactly the kind of mistake we're spending this whole video correcting. And it happened to a close relative of Dimetrodons, for almost identical reasons. Meet Edaphosaurus, another sail-backed animal from roughly the same time and place, which gets mistaken for a close Dimetrodon relative constantly, purely because of that shared sail. It's not. Edaphosaurus sits in an entirely separate family, evolving its own tall dorsal sail completely independently, a genuine case of two distantly related lineages arriving at a similar-looking structure through parallel evolution rather than shared ancestry. The exact same broad phenomenon behind Dimetrodon's own serrated teeth, showing up convergently with theropod dinosaurs. And the two animals could not have been more different in how they actually lived. Edaphosaurus was herbivorous, one of the earliest large plant-eating land animals known, equipped with a mouthful of small, blunt, densely packed grinding teeth, essentially a built-in dental pavement. Its genus name literally translates to pavement lizard, a world away from Dimetrodon's sharp, differentiated, occasionally serrated predatory bite. Here's where it gets genuinely remarkable, and it's a story worth knowing in full. Back in 1886, Edward Drinker Cope, the same paleontologist who'd named Dimetrodon less than a decade earlier, described a set of unusual sail spine fossils under an entirely separate genus name, Neosaurus, meaning ship lizard. The problem was, no skull had ever been found attached to that particular skeleton, so when Cope, and later the American Museum of Natural History, under its president Henry Fairfield Osborn, mounted the Neosaurus skeleton for public display, they made an assumption. Since it had a sail resembling Dimetrodon's, and Dimetrodon was a known predator, they topped the mounted skeleton off with a carnivorous Dimetrodon-style head. A plant-eater's body wearing a predator's skull, presented to the public as a single, coherent animal. That mistaken reconstruction got reproduced in illustrations for years, including a well-known 1897 painting by Charles R. Knight, one of the most influential paleo-art illustrators of the era, meaning generations of museum visitors and readers saw a fabricated hybrid animal and had no reason to question it. Researchers, including E.C. Case, identified the mistake as early as the early 1900s. Once Neosaurus was properly recognized as Edaphosaurus, wearing the wrong head entirely. But the corrected picture took decades to fully catch up with the original mistake in popular sources, some of it lingering into the 1940s. A sail-backed animal, wrongly assumed to be closely related to Dimetrodon because of a superficial resemblance, ended up with an entirely fabricated identity, publicly displayed as fact, for the better part of half a century. It's honestly a fitting place to land, given everything else in this animal's own story. A genus first found and misidentified under a different name entirely. A second specimen sitting in a museum drawer for over 150 years before anyone figured out what it actually was. A sail whose real purpose is still being actively debated by the people studying it right now. And a close relative that spent decades on public display, wearing a head that was never actually its own, for the exact same reason people still call Dimetrodon a dinosaur today. A recognizable silhouette, mistaken for a familiar category because nobody stopped to check. Alright, since we're apparently on a real streak of prehistoric animals with misunderstood anatomy, next time we're covering a genuinely famous dinosaur with almost the exact same kind of unresolved debate attached to its most recognizable feature, plus a naming story just as strange as anything we covered today. Stegosaurus and the plates and spikes running down its back and tail, structures so mysterious that one of them is officially named after a joke from a newspaper comic strip, and the joke name stuck for real in actual published science. That one's next. Let me know in the comments what you want cataloged after that, and subscribe to Claw Catalog so you're here for it.